Hi, my name is Mariano Zaron, and in this video I'm going to show you the optimal way of evaluating Chebyshev objects. So let's do a brief recap of something that Ignacio was talking about in another video when he talks about the core of Chebyshev theory and that we use in our library. So if we want to approximate a function, so we've got a function here, say one-dimensional just to illustrate the point, what we have to define is set of points here, and then we evaluate that function on those points. That's the only thing that we need in order to build a Chebyshev object, which in our library is called a Chebyshev mocex object. Now, if you remember, Ignacio spoke about two important polynomials that we look at. The first one he denoted by Fn, which is I'm going to denote it by the sum of fi, not fi's. He used coefficients ai. So I'm using the same notation that he used in case you want to go back to that video or you've seen that video recently. So what is this polynomial? This polynomial is called the truncated Chebyshev series. So one of the important things about the theory, one of the cool things about the theory of Chebyshev is that if the function f behaves relatively well, then we know that the Chebyshev series converges to that function. And of course, the nicer the function f, the better the convergence is, to the point that if f is analytic, we've got exponential convergence. Great. And we know that this polynomial here, as n increases, converges exponentially to f. Along with fn, which is called the truncated Chebyshev series of degree n, we've got the interpolant to that function on these points. I'm going to do it exaggerated here, but this is the dotted line is the polynomial which interpolates f at those points. Of course, if these are the Chebyshev points, you're not going to get this, you're going to get something really accurate. But this is how you distinguish between the two. Here then, Ignacio wrote it in that video as the sum of ci's cix. So this expression again uses Chebyshev polynomials as the basis for the space of polynomials of degree at most n. These are the coefficients that give you the Pn, which is the interpolant. These are the coefficients that give you the truncated Chebyshev series. Now, these two converge exponentially to f if f is analytic. So that was kind of the key idea from that video. The important thing to note is that between the two, to be honest, you don't really care which one you use. They converge virtually at the same time. But the difference is that evaluating this expression up here is not 100% trivial, while evaluating this one is much more amenable. And what I'm going to talk about in this video is a way, what we consider to be the optimal way of evaluating this polynomial over here. So, as I said, what do you need in order to build a mocex object or a Chebyshev object? The only thing that you need is to find the interval of approximation, take the points, Chebyshev points here, these big x's, take the corresponding values, and that's all you need. So I'm going to write it down up here. x0 all the way to xn. And then the corresponding values of f on these points are going to be the v's. v0 all the way to vn. Now, instead of expressing the polynomial in terms of Chebyshev points, I'm going to express it in terms of the different bases. And the base is going to be given by the Lagrange polynomials. So written in that way, it looks like this. There's no accident, but the coefficients here, the v's, are the same as these values over here. The reason is the definition of the Lagrange polynomial. So Lagrange polynomials are defined with respect to a set of points. So if, for example, we're only interested in 3 points, for argument's sake, let's say this one, that one, and that one. We're going to have 3 Lagrange polynomials, the one corresponding to that point, the one corresponding to that point, and the last one corresponding to that one. The one corresponding to that one is worth 1 at that point and 0 otherwise. So it would be something like this, kind of. but you get the idea. The point is that is worth 1 if x is equal to xi, but if x is not xi, but it has to be one of these other points, then it's going to be equal to 0. Okay? And the definition of this Lagrange polynomial is this is j different from I over x minus xj. This is, sorry, I here, j different from I. So basically, this here is just a coefficient, and this here is one that carries the variable x. And you're taking the distance or the difference between x and all the other xj's, so not with xi. So that defines this Lagrange polynomial. And its definition and main property, which is this one that I showed here, allows us to come up with this expression, which is very important. So if we were to just evaluate this expression, which we could in principle from this information, because we don't need to do anything in order to obtain it, is once you've got the x zeros and the xi, sorry, and the vi's, you've got this expression. If you were to evaluate it directly, it has a complexity proportional to n squared, where n is essentially the size of the set of these points, which could in principle be the Chebyshev. Those are the ones we're interested in because of the exponential convergence, but it could be anything else. It could just be a collection of points in general. And if you want to evaluate this polynomial that results from these two bits of information, this takes or has complexity of proportional to n squared. The reason is that you've got here, you didn't write it, but we've got n summands, and each summand involves evaluating a Lagrange polynomial. And each Lagrange polynomial involves taking the product of n things. So that's why you have something of this sort. Now, that is not that bad in principle, especially if you're in one dimension and the n is not that big. But what happens when you go to higher dimensions? I'm not going to cover that case in this video, but what happens is that expressions like this, you'll have to evaluate them many times in order to come up with one single value of the corresponding polynomial Pn. So in that case, it becomes a bit more costly. Also, if n increases, then you start seeing the cost of having something of the type n squared rather than something less. So the question is, can we do better? And we can. And what I'm going to show you is a sort of quick derivation. I'm not going to include all the steps, but a derivation of how we obtain a formula for evaluating this polynomial Pn called the Barycentric interpolation formula, which is the one that we've implemented in our software. Any details that you want to check, so any more specific details that I don't cover in this video that you want to check, I suggest that you go to the book that Ignacio already recommended, which is called Approximation Practice Theory and Approximation Practice by Professor Trefethen. I think what I'm covering here is in chapter 4 and 5, or one of the two. Therein you'll find many references and more details of everything that I want to cover here, but I just want to cover the essentials and give you an idea of what all this involves. So let's see how we can derive the barycentric formula. So starting from this equation and defining the following two terms, mu I is just going to be basically this coefficient, or 1 over that coefficient. It's 1 over the product, xi minus xj. We're running over all the j's different from I. And we define L of x to be the product of x minus xj. Then we have the following thing. I'm just going to rewrite, first of all, using these two definitions, I'm going to rewrite this expression. And what we obtain, I'm going to write it over here, is the sum of vi's, mu I, and then the product of x minus xj, where j is different from I. Now, This step is immediate. It's just basically replacing this mu I into there and taking what is left. The next step, which is perhaps I'm skipping a few steps here, and maybe you won't be able to see it straight away if you take it to the side and try and work it out. I'm sure that you'll be able to deduce it. But this is equal to L of x times the sum of vi's, mu i's over x minus xi. Now, this equality here is crucial because whereas this expression over here has complexity when evaluating proportional to n squared, this has linear complexity, which is a big difference. I mean, notice that L of x is just the product of these n terms, and then we've got n summands, each of which has only a couple of operations. So that's why it's proportional to just n. So this is already a big step that reduces the cost of evaluating these objects, especially when you go to higher dimensions, quite a bit. And this expression can be further modified to obtain what we call the barycentric interpolation formula, which is the following thing. Vi mu I over x minus xi over the sum, and there's going to be there's not going to be the I, sorry. There's just going to be mu I over x minus xi. So this over here is the important one. So it has this degree, this complexity in terms of the cost of the valuation. And if you notice, the only thing that it involves are the xi's, which you already have, the vi's, which you already have, and these terms mu I, which are these ones here, only depend on the xi's. And you can compute them beforehand, even before you obtain the vi's, by the way. So they don't really add any cost once you've computed these vi's. If you do this on site, then at evaluation time, this is going to run really quickly. But this particular formula, which applies to any collection of points x0 all the way to xn, regardless of the way they're distributed, simplifies even further when we are using Chebyshev points to having mu I being equal to minus 1 to the I. So there's nothing that you need to be computing beforehand. The mu is very simple. Just comment, this term has to be multiplied by a half if it's either the first summon, so if it corresponds to x0, or it corresponds to the last one, so xn. Otherwise, it's just minus 1 to the I. So basically what we have is a very simple formula to evaluate this polynomial over here. Very quick, great so far. So let's summarize what we have so far. So given the function f, when you evaluate f on the Chebyshev points, you obtain a set V. We know that the truncated Chebyshev series, denoted by Fn, and the Chebyshev object, which is the Chebyshev interpolant, denoted by Pn, both converge to f exponentially as n tends to infinity. But just starting with the set V, you can obtain the following expression for the Chebyshev interpolant, which is given in terms of Lagrange polynomials. So calibrating the Chebyshev object, which means obtaining an expression for it, can be done immediately because it only involves the values vi's, which you obtain when you evaluate f on Chebyshev points, and on the Lagrange polynomials that only depend on the geometry of the points chosen for the sets x. And the most important step, once you've got this expression, when the points are Chebyshev, then we obtain the barycentric interpolation formula in this way, which has complexity when evaluated proportional to n, which is essentially as fast as you can expect. In the following video, I'm going to talk about another very important property to do with the barycentric interpolation formula, which is its numerical stability when it's implemented in a computer. At first sight, you may wonder whether there is any stability given that you have denominators where x can approximate as much as you want the values xi. But we'll see that there's no issue regarding the rounding off errors that sometimes take place in computers, and that using it is completely safe. Thank you very much for watching this video. If you've got any questions, please get in contact with us. See you next time.